Yeah, so that's me, Javier. My Twitter account, in case you want to complain about the talk or you have any questions, anything, you can find me there. So I'm going to be speaking today about time series databases. And first thing, why I want to speak about databases. And the reason is because I've been really working with databases for a long time. Over 30 years working in some way or another with databases. So I was an early user of NoSQL because when I was running databases on my Commodore Amiga or my Aston CPC, there was no way to run a SQL database there. So it was like, different things. Then I started using a lot of relational databases, Oracle, Sybase, Informix, MySQL, Postgres, whatever, as a web developer. Eventually, I started working more and more with data. I started playing with things like Redis and MongoDB, different things. I moved to proper big data. I spent 3 years, almost 4 years actually. I'm trying to forget, but I spent over 3 years working at Amazon Web Services, and there I was a specialist on data, so I was working with many types of different data technologies. And now I work for an open source company. We are developing an open source time series database. So in these 30 years of working with databases in one capacity or another, I've developed some intuition about when you could be using a database or another for different types of problem. And today I'm going to be speaking about that. But before I speak about databases, I want to speak about timestamps and working with time in general. I think we all agree that working with timestamps can be hard. Who here have never had an issue with time zones? They are super tricky. Working with time is always kind of, I wish I had thought of that joke, but it's actually quite cool. So time zones are tricky. And the thing is, I don't know if anyone here, I know you are a very, cultivated audience, so surely someone here can tell me what happened in China almost by midnight, 1927. Of course, you all know what happened. It was not exactly at this particular second, but what happened is like, when the year was about to change, for whichever political reasons in China, they decided to go back by 5 minutes and 52 seconds in the clock for their time zone. So that seems like, oh, that's cool for a pub quiz. But what happens is that if you're using Java and you try to subtract that particular second with another second, the difference is going to be 1 second. From the second, you can find these things. Stack Overflow is awesome. So if you try to subtract this second, 0.08 from second 0.7 of this particular date, you're going to be having, depending which version of Java you are using, you're going to be having 353 seconds difference instead of 1, because that happened, even if you're not using any time zone. And if you don't know about these things, things that what I mean here is like working with timestamps is tricky in general. Just with timestamps. That's why we use epoch. So that's an epoch, seconds that pass since January 1st, 1917. Of course, you all know which date is this, yeah? If you prefer a more human representation, this is the date. What is that? Is that the 1st of April of 29, or maybe 1899? Or is the 19th of April of, the year 1? I have no idea. So as I am saying, working with times and timestamps, it's not straightforward. There are many, many, many pitfalls when you're working with time. And I'm just speaking about timestamps in general. When you try to work with timestamps on a database, you get newer and more interesting problems that maybe you haven't found, but maybe you are not aware of. Specifically, if you are trying to analyze data which is changing over time, or if you are working with data at large scale or at high rate. That's kind of the, what I want to be talking about today. Which kind of databases we can use for working with data at large scale, or when data is moving fast, or when you want to reason, about data. And before I start speaking about time series databases, I don't hate any database. There is one specifically, only one, that I might not hate, but heavily dislike. But I'm not going to say which one, but because maybe Larry Ellison is watching this. But I don't really hate. I don't really hate any databases. I really like them, and I always say, if you can solve your problem with a relational database, it might be Postgres, it might be MySQL, maybe Oracle, Sybase, SQL Server, SQLite. I don't really care. Any database which is maintained, relational databases are great for a lot of use cases. The thing is, they are not optimized for any specific use case. They are great, they are transactional, you can do everything in relational databases, but they cannot really specialize for specific use cases. And there are some things that relational databases are not really great when you are working with them because they are not designed for that. For example, on a database, if you want to get reasonable performance in queries, you need to have indexes. That means after data is being written, you need to write again to some indexes in order to read quickly. That's cool for most use cases, because in most use cases, you write some data and then you read many times. But what happens if you are ingesting data very fast, maybe faster than you are reading? Then if you have indexes, they're going to have write amplification. They are not designed for that. So for that use case, having a relational database might be tricky if you want to have good read performance. Same thing, like in a relational database, you cannot really ask the database, hey, how many rows per second are we ingesting? Are we finding any gaps in ingestion for a particular table? They are not designed for that. You want to do those things, you're going to have to engineer a lot of things around that to solve those specific questions. Relational databases today, they are very capable. If you have a few, depending on the database, but many databases are comfortable. If you have a few 100 million records, that's fine. Few 100 millions. When I was, a few years ago, I would have told you a few millions. Today, 500 million records, yeah, I can move them. That's fine. What if you have billions of records? A relational database is not really designed for that. You can use it, of course. Facebook works on top of MySQL. You can build anything on top of a relational database. It's also about, how healthy mentally you want to stay and how many resources you want to dedicate to those things. Or just working with sparse data. If I think of a table in a database, I think of a table with a few columns, maybe many columns, maybe up to 100 columns. If I get to a new project as a developer and I find a table with more than 200 columns I've seen that. I've been working in banks, 200 columns, still fair game. But that's kind of the thing, because a relational database, even if you have indexes, then they have to be accessing row after row of data. It's not ideal. So they're not really designed for that. But some people, they have some specific use cases in which they need to have much more than 200 columns. It might happen. And sometimes people surprise you. Just we technically, at the database I'm going to be talking about today, we don't have any theoretical limit for how many columns you want to add to a table. Theoretically, we can move anything. But in practice, there are some limits. And just a couple of weeks ago, someone in our public Slack was asking, hey, I'm having some issues. I have this table, and it's working fine, but now I'm trying to do something, select star whatever, filtering, removing duplicates, ingesting another table. I'm having a lot of issues. And he said, this is my table. Like, yeah, I only have not even 2,000 rows, 6,000 columns. 6,000 columns! 6,000 columns in one table. Yeah? And the cool thing is like, it's working fine for some things, but with select star, it's not. That's the thing. We select a star, 6,000 columns, like, and he was doing an inner join and whatever, and that's cool. I mean, he was assuming, that we will be able to work with this, and actually we are able to work with this, just not with select star, because we don't store the data in rows, we store by columns. So even you have 6,000 columns, you typically access maybe 5, 10 columns in one query. We only have to access those columns. We don't need to access the others. So we don't really care. They take space on the disk, but we don't really, when we are reading data, we don't really have an issue with that. But that's what I mean. If you want to have a table, maybe not with 6,000 columns, but 2,000, which is something we see quite often, a relational database is going to tell you, I don't know, that's kind of the thing. So that's the idea. Relational databases, very comfortable. They look very, very familiar. They are very cool, but sometimes they are not ideal. Welcome. Yeah, thank you. Yeah, I know you are here. It's a very good talk. So if you ask me, so maybe it's a small audience. I have to. What's this number? Seconds in a day. You are good. This one. Seconds in a week. This one. Seconds in a month, more or less, because a month is tricky. See, 28 days is 31 days. So an average month has like 30.42 days. So that's, that's the number of seconds in 30.42 days. So that's kind of the thing. So now you have this number of seconds in 1 month. So now imagine that you have a factory floor with 500 machines, or 500 people with a mobile phone, or a small fleet of cars, or motorbikes, scooters, or 500 vehicles, or you have like 50 trains with 10 wagons, and each of those is sending you a data point every second. So that's the thing. Only with 500 devices, which is actually a very low number, you are getting in one day 43 million rows. And now your database starts crying. It's like, okay, yeah, I see what you mean. So just 2 days of data, we are getting close to 100 million. If you get only one sensor per second, on only 500 devices. Some of our users, we are an open source database, so I don't know all the users, but some of them I know. And some of them, they are managing fleets of vehicles. They are sending data in real time of about 10 sensors, temperature, speed, pressure, whatever, latitude, longitude. So they're sending data of about 10 seconds, about 10 sensors every few seconds, and they have 2 million vehicles worldwide. So that's the thing. When you have this kind of data, it starts to add, and it's like, okay, how do I work with data which is coming at this volume? That's kind of the thing. And what I wanted to tell you, and this has been a long intro, but now I'm going to start. Actually, I'm going to have demos, I'm going to have code, I'm going to have stupid things. But this was like kind of a long intro to what I'm going to be talking about, which is not all the data problems are the same. So when you are using a relational database, you can use it. Relational databases can be used for pretty much anything, but there are many other types of databases because there are many different types, many different patterns of working with data, both for storing and for ingesting data. There is a website. It's called DB Engines Ranking, which is quite cool. It's like a popularity contest of databases. So they keep track of the popularity of databases. I mean, it's not very scientific. It's social media mentions and publications and whatnot, but it gives you an idea of what's trending. And last month, which is last time I updated this screenshot, they were tracking over 400 different databases. Almost 40% are relational, but about 60% are non-relational databases. They might be document databases like MongoDB, key value stores like DynamoDB or Redis maybe. They might be graph databases like Apache Tinkerpop or maybe like Neo4j, or they might be time series databases, which is what I want to talk about today. Actually, they are tracking 43 time series databases, which is not too bad. There are more, but they are tracking 43 of those. It's a bit tricky because, some databases are multi-model, so they can do different things. Some are properly time series, but you have 43 databases at least that have a specific engineering semantics that has been especially designed for dealing with this type of problems. And actually, they are getting popular. If you see here, let me just make this better. So this line here is how time series databases have been trending. This chart is very tricky because trending means they change in popularity. So relational databases are here, they're almost flat. They are the most popular, but it's almost flat because they've been as popular for the past 10 years. But actually, graph databases and time series, they have been trending quite a bit. We are not, I'm going to speak today about QuestDB, which is where I work. We are not the most popular time series database. Most popular will be InfluxDB, Timescale. Actually, there's someone from Victoria Metrics, which is talking in the whole one, which is totally unfair because I think we are cooler. But Victoria Metrics is a cool database. So there are many time series databases out there. I want to speak about QuestDB, which is where I work. We are fully open source, Apache 2.0 license, so you can do anything you want with the database. As long as if you don't like how it works, we don't accept any responsibility. You cannot take me to trial because we don't work exactly the way you want. But other than that, you don't have any limitations. Fully open source. We are fairly popular. I mean, we have now over 1,000 stars on GitHub. We are a small team. I mean, the QuestDB team ourselves, we're about 20 people, of which not all of us are contributing to the core. but we have over 100 contributors in the community. We have releases every 2 or 3 weeks. The project itself has been around for about 8 years, but the first year was like mostly a solo project, just one-man project. And for the past 2 years, we've been actually, it was open source, but didn't have like any external contributors. For the past 2 years, we've been actually getting more momentum. That's kind of the idea. I just joined QuestDB a year ago. This week has been my anniversary in the company. So we are QuestDB, and we like to be known because we really are performant. I'm going to show you what I mean by performant. And we try to be performant also with small machines. I always say that it's kind of easy to perform very well if you have 200 CPUs and 2 terabytes of RAM. Yeah, and a fast hard drive. Then you can perform fairly well. But performing well on small machines, that's a different beast. And we try to perform reasonably, within reason, well in a small machine. We also want to offer a good developer experience. We try hard to give you a good developer experience. Actually, that's why they hire me. So I can have like more contact with the communities, and I try also QuestDB myself quite a bit for doing integrations and demos, and I always like telling the team, hey, I would like this to be, hey, I would like this to be. Eventually, I commit some code to the repository myself, but I'm not great at that. But yeah, we try to have a good developer experience, and we are open source, and we intend to keep being open source, no changes to our license whatsoever. So before I start with the demos, how do I know if I have a time series problem? Well, it might be for many small things. It might be because maybe you have a use case in which you find yourself that are inserting data and you almost never edit or delete data individually. It's like, oh yeah, I just keep adding data. When you keep adding data, it happens what I told you before. Your data starts growing up to a point that you wouldn't be comfortable with your operational database. And sometimes, since the data is growing, you have to delete your data by not just because it's old. It's something I wouldn't do on my database. Imagine I'm, I don't know, I'm Netflix or an Amazon or I'm whoever they're working with, and you say, hey, this user has been with us for 10 years. We have too many users. Let's remove this one. It was the first user, but it's too old. You don't do that usually on your on your database. But on analytics, on the kind of things we do, you do that. Like, oh, the sensor data I ingested 2 years ago, it's good for nothing right now. So I can just move it to cheaper storage, delete it, whatever. Also, being fast at querying, but also at ingesting data, usually is critical for your business because you want to work with real time. When you're reading data, most of your queries are scoped around a time range. It might be, give me the average, maximum, and minimum exchange rate of this particular currency for the past minute or the past week or the past hour. It might be, tell me what happened within the 10 microseconds before and after a particular incident. We go down to microseconds in our database. So tell me what happened in the microseconds before and after a particular incident. It's not usually that you do a select star from a database without any time bound. Usually you are scoped to a particular time range. And in that time range, usually, recent data is more interesting than other data. I'm more interested in what happened. Recent might be a few seconds, a few days, a few weeks, few months. Other than that, data might be interesting, but not as interesting. Same thing, very often, you maybe are getting data at very high frequency, every few milliseconds, every few seconds, every few minutes. But in reality, you are then doing analytics maybe in, I don't know, every 15 minutes, every day. So you need to resample your data and work with those things. Or you need to align different time series that happen at different moments in time. And in many use cases, you are powering real-time dashboards. And by real-time dashboards, I mean things like those, for example. This is an example of Apache Superset. It's an Apache tool for for creating charts, similar to Tableau, to Looker, all those things. So this is just like some charts powered by QuestDB on top of Apache Superset. This is batch data, but this is actually streaming data. I've been during the previous talk, I've started a script which is sending data to the cloud of QuestDB. We have a cloud offering, so it's sending data to the cloud, and this is a chart that is refreshing every 5 seconds, and it's live data. I'm sending a simulated trading data about the exchange of Ethereum and Bitcoin and the US dollar. So this is like a real-time dashboard that is updating. So, very often you have to do these kind of things. So the database you want to use for those dashboards, very often you want it to be a time series database. So when we are talking about time series databases, I've been speaking about speed and fast, all the time. The main reason is because it's been a long time, a very long time, since the last time a user told me, can you make this query slower, please? No? They often ask me if I can speak slower. Yes, I get that a lot. But not about the queries being slower. Or can you make ingestion on the database slower? I would like to have more time between when you ingest the data and I can actually use it. It doesn't happen. People really prefer things to be available as fast as possible. So when we're talking about the speed, I could show you some benchmarks, but all benchmarks, if I tell you my database is the fastest open source time series database, which I believe it is, every other vendor is going to tell you exactly the same, and we are all going to be right. So that's about it. So I don't want to enter in a competition who is faster. I just want to show you some numbers of some things our database can actually do. So we have some blog posts published with all the details if you want to reproduce that we can ingest over 1.4 million rows per second. This is actually quite old. It's 2 years old. Now we can ingest much more than that. At the same time, we can query data at a rate of 4 billion rows per second, scanning data, with 16 CPUs. So you need to have a reasonable machine. We use a benchmark which is specialized on time series. We didn't write this benchmark, but we maintain a fork, but we didn't write it ourselves. It was written first by InfluxDB, then it was maintained by Timescale, and since lately it's not very well maintained, we decided to fork last week. We decided to fork ourselves. Yeah, because some other people like ourselves, but also people from MongoDB, they also offer time series module. They have some pending patches, pending pull requests, having there for months, so we decided to fork. It's a pity, but it is the way it is. We have, the new numbers we have are a bit better. So QuestDB, as of 2 months ago, we actually, with 16 CPUs, we can ingest over 4.3 million rows per. When I say a row per second, it doesn't mean anything, because a row with 6,000 columns is going to be way slower to ingest than a row with 2 columns. So in this particular benchmark, the rows have 10 strings and 10 numbers. So it's 20 columns, 10 metrics, 10 dimensions. So with that shape, we are able to ingest over 4 million records, on a single machine, on a single instance. Other databases, they on the same benchmark, they perform not as well. Still is quite impressive. 500,000 records per second, 300,000. I mean, just to put it in context, I don't know of anyone, absolutely anyone, ingesting 4 million records per second in a sustained way. The user that I personally know, personally in these days means like, I send a Slack and an email, and once I saw them on Zoom. So, but the user I personally know that using QuestDB in a heavier way, they are ingesting about 150,000 records per second every second of the day, but it's only 150,000 per second. So 4 million records is pretty high, but that's kind of the idea. We have an interesting story, and my colleague Andrew, which is quite smart, he wrote just last week, he published a blog post about this. We had an interesting story. When we were benchmarking the newer version of the database, we found that we were changing some things, and we found out that we couldn't ingest faster than 2 million rows per second. And that was interesting. First, because the number was like 2 million rows per second, kind of. And second, there was not like a lot of variation in that number. And usually on the benchmarks, just to be some variation. And second, because we thought, our intuition was saying, we should be way faster now. So we found out the benchmark itself, it couldn't produce data faster than 2 million per second. Which was fine in the past because, no database could accept that. So it's like, yeah, we are benchmarking with something that can send. So we have to re-engineer the benchmark tool to actually send more data. And it's when we found out we can actually go over 4 million, that it's faster than we thought. But, these things are interesting. But I digress here. You might be telling me, okay, Javier, I don't really need 4 million records per second. And no one needs 4 million. That's cool. Because you're not going to get them. This is a benchmark. You know what I mean? Yeah? I told you it's a lie. You're not going to get 4 million rows per second. I tell you, oh, my database can do this. Yeah, of course it can do this. You have 16 CPUs for writing, 16 for reading, reasonable memory, super fast hard drive. You cannot get 4 million rows per second on a cloud instance ever, because cloud instances, they give you this. It looks like a disk, but it's not really. It's like a networking. It's a networking device. You have a lot of latency there. When you are doing like even a very demanding web application, you don't care about those things. When you are doing data or intensive writing, then you notice the latency. And on a cloud drive, I mean, if you want to do that, you can use something which is called a local SSD. That, of course, all the clouds, they offer them. The challenge is like when you restart your instance, you lose all the data, which is not the nicest outcome for a database. So, in cloud, it's very tricky to get over a few, even tens of thousands per second. It's kind of tricky on a single instance. So you're not going to be getting 4 million rows per second, But the thing is, when we are optimizing for 4 million rows per second on a good machine, it means in a decent machine, you can get actually good performance. So something we hear often when people are moving from other databases to QuestDB is that, oh, it's cool because, in the other database, sometimes we're slow, and here we are using smaller machines and it's faster. That's kind of what we are trying for. It's like, yeah, no one is going to be using the 4 million per second, maybe on batch, but not really on streaming. But, that means we are also faster in a smaller machine. How fast? I'm going to show you on this machine. And I'm not going to be closer to 4 million, by the way, because, in this machine, I don't have 16 CPUs. I'm running a lot of other things, containers and other things at the same time. So I'm not going to be getting even close to that. But there we here. When you see here, I'm just going to be, I have 3 terminals. The 3 of them are going to be starting the same Go application. So basically, I'm now sending from 3 different Go applications so I can saturate my database. This is the log of the database. It's ingesting data like crazy. So what I'm doing here is I have this, on QuestDB, you can ingest data using the Postgres protocol, but for inserting data, Postgres is not very fast, the Postgres protocol. So we have an alternative protocol, and we have clients in 7 languages, in C, in Rust, in .NET, in Python, in Java, in Node.js, and in Go. So yeah, 7 languages. We have official client to ingest. If you're using Ruby or PHP or whatever, you can just, also send data using a socket. But here what I'm doing is like, I'm generating some random data. I'm in a table called ILP test, and I have 1, 2, 3, 4, 5, 6, 7 columns. 6 of them are numbers. The other is just a string. So I'm generating, each of those scripts was sending 10 million records. So I should have now, I've ingested 30 million records in about, sorry, I was worrying. I've been ingesting 30 million records in about 10 seconds, okay? So let me just show you. I'm going to the web interface of my local database. I ran this before, so I have already 30 million rows from before. So if I now select count from this table, I have 60 million rows, okay? But the interesting bit is when I run this query, I will tell you more about this query later in the presentation. But basically in this query, I'm going to be running aggregating per second. So it's going to tell me how many rows I was ingesting at every particular second in the last 10 seconds of the ingestion. So it tells me in this second, I was ingesting slightly over 2 million rows per second, 2.2 million, 1.8, 1.2, 1.9. So yeah, it seems I'm not getting over 2 million records per second, which is not too bad, but it's not the 4 I was telling you. So benchmarks are lies, but they give you an idea what you can get. Are you still with me here? Cool. Because I'm going to start speaking about querying data now. Let's see if I can find my screen. Sure. Yeah, we accept when you query data, we use SQL, unlike other time series databases, and we use the Postgres protocol. So you have like any library. Any you can use PsychoPG, you can use JDBC, you can use any library that's actually the dashboard I showed you, this one. This is just a Grafana installation, and that Grafana is we are using a Postgres connector. I'm just telling my Grafana discard the changes, and just tell me Grafana, oh yeah, this is a Postgres, a Postgres database. It just lives in this port and this particular password, and Grafana believes in a Postgres, sends me the queries, I reply, we are fine, no one needs to know we are not a Postgres. So we have some extensions. We don't support the whole SQL, the whole number of functions from SQL, and we offer our own extensions, but at the protocol level, that works. Thank you. So ingestion is one thing. Querying performance is another thing. We have this machine. It's always open. It's always available. Demo questdb.io. On that particular instance, it's an instance running on AWS. It's fairly big, but it's served by many users. But it's a fairly capable instance. And in this instance, we have a few open data sets. One of them, the trace dataset, is a live dataset. It's getting data, new data every second or so. The trace dataset is getting data from the Coinbase API, and we are getting data from the real data from Bitcoin and Ethereum exchange with the dollar. The other datasets are batch datasets. One I like is this one, the trips dataset. You might be familiar with that because it's used by many people on the working with big data. It represents taxi rides in the city of New York. And for its taxi ride, we have about 20 columns, something like that. As you can see here, the type of the cab, which is the vendor ID, at which time the trip started, when it finished, latitude, longitude of start and finish, how many passengers, the distance, the amount, the tips, the tolls, whatever, blah, 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 blah. So you can have, like, you see here many different columns. And the interesting bit is here at the bottom. We have 1.6 billion records in this table. 1.6 billion records, American billions. So it's not like, still. So it's only 1,600 million records. Not that bad. So 1.6 billion records, sorry. And I'm going to do something interesting. I believe it's interesting. I don't know you. So I'm going to say something like, tell me how many records I have, and give me also the average of one of these columns, for example, one that is, the fair amount. Okay. So I didn't tell you, we don't use indexes on QuestDB. We don't believe in indexes for this kind of data. And we don't use any cache. So I'm going to run a query that is going to scan 1.6 billion records, and it's going to calculate the total count, that's easy, and an average. How long do you think it will take your database to do an average of one column over 1.6 billion records? Which database are you using? No, in my database, that's super fast. That's not going to happen. I mean, I wish. But on your database, how long do you think this will take? Well, a second only. That's a fast database. In ours, which is pretty fast, it takes almost half a second. I know it's terribly slow. I promise you a fast database. It's very slow. There are many things here. First, average is a complex calculation. If I do a sum, it's actually way faster. Summing, just adding data is faster than adding and then dividing. So it's only 100 milliseconds. But still, it's quite slow. Why? Because this is not a time series query. This is just an aggregation query. We don't have any time range here. We are not doing any time operations. It's a full scan of the database. Usually, we don't have that type of query. What you usually have on real life is things like, okay, I want to have this where, for example, where the date is in the year 2016, 16, and that's faster. That's already 24 milliseconds. Why? Because we only have to scan 146 million rows, which is nothing. So that's the idea, When and of course, if you start not only for the whole year, if you go only for 1 month, no, I want to see how many, the average for 1 month of data. Oh, 4 milliseconds. No, only in my birthday. Okay, so in my birthday, it was only, it takes me 1 millisecond to calculate the results of, it's still, this is actually quite small. It's not even 500,000 records, but you get the idea, yeah? So that's the thing. When you are doing a time scope query, it's kind of fast. So that's the thing. That's that's why I wanted to show you that we are quite performant on reading and also on writing within reason. So now I want to talk about the second part for the last 10 minutes. I told you I was going to use the whole time. So performance is just one part of the equation, but usability is the other. which is also why some people prefer to use time series databases, specifically QuestDB, but also the time series databases make your life easier. Because having time series semantics is critical when you have to run this kind of queries very often. The first one, I saw you already in the demo, you didn't notice, but in a conventional database, if you want to filter the data for one particular year, you need to do something like, oh, I want to call the function year over this date, where the year of this date equals whatever. Or you have to do, depending on what you have to do. But we have some this extended semantics on QuestDB, in which you can work with time ranges at any level of precision up to microseconds. So we can just use the in for that thing, and you go only to what happened in this month, in this year, in this second, in this millisecond, in this microsecond. But we can do better. It's like, tell me what happened in starting 2018 and 2 months. So this will be only the first 2 months of 2018. Again, you could do that in a database with between, but you know, for relative dates, make your life a bit easier. Or for 10 seconds, or I want the whole of 2018 minus the 3 last days. Oh, that's interesting. So those kind of things, you know, we have them in this weird semantic, but when we have to do it very often, it makes sense. And we have even more interesting things. This one is telling me, bear with me here, I'm starting at the second 58 or before midnight of this particular day. And I'm telling QuestDB, I'm going to explore for this second and 4 seconds in the future in intervals of 1 day for 7 days. And I can do this also, you know, backwards. Let me just show you that on the demo site. You can try all of this, by the way, on the demo site. You can try it now, you can try it at home. Most of you will never try it, and I will be very sad for that, but that's okay, because, you know, I cannot see you well, so I cannot do revenge. This is the demo site, yeah. So what this is doing is picking this date, and it's going 7 days minus, so 7 days in the past, and it's going to take the second from the 58 and 4 seconds more. So as you can see, this is 7 days before that date, starting second 58 until second 02, and then it's going to the next day. And as you can see, this is quite powerful semantics for things that you do all the time in relational databases. I have this incident, I want to know what happened before and after for, you know, in intervals. And these intervals, you know, I here work with days and seconds. You can go with months, with years, with microseconds, milliseconds. You can combine a number of units here. So you get the idea, yeah? Nothing you cannot do on a relational database, but this, apart from performance, make your life a bit easier. Your queries are smaller. That's kind of the thing. We also have sample by. And I also show you an example of sample by. Sample by is like group by, but rather than grouping by a number of columns, I'm grouping by some time units. For example, I have some data set, it's also available on the demo site. It has some weather information in Manhattan for a few years, and we have about every minute we have like 2 or 3 entries not every minute, every hour, sorry. Every hour you have 2 or 3 metrics, because weather doesn't change. If you live in London, maybe yes, but in other places, weather doesn't change that often. So just, you know, a couple of entries per hour is more than enough for this demo. So here what they are doing is like, okay, I want to have the average, but sample by month. Even if I'm getting the data, like, you know, in 2 times per hour, so this will be sample by month. Or I have this one which is a bit more interesting. This is on the trading data set. I'm saying I want to do the volume weighted average, which is basically dividing the total amount, the price by the amount, dividing into the total amount, and this is the volume weighted average. So these aggregations, I'm going to do them with some filters for the past day and in 15 minutes intervals. So basically what this is doing, I'm going to go to the demo site, sorry. I'm going to go to the demo site and execute this one. What this one is doing is going to take, in this data set, I'm getting data every second or so, but now what it's doing is giving me data in 15 minutes interval and give me the aggregate in 15 minutes intervals. That's, you know, that's what I'm doing here. It says here align to calendar because I want to start at the top of the hour. If I don't use this, what will happen is that it will align with the first timestamp I have. So the first record came at that particular second and millisecond, and then it's moving in 15 minutes from that one. Usually that's not what you need for analytics, depending what you are doing. So we have this align to calendar that allows me to actually, start at the top of the hour. We also support with offset, time zones, all those things. So, oh yeah. Sorry. Oh no, I was not taking 2 seconds. Thank you. It was just just for, but thank you very much. So bear with me here. Have you ever tried to tell your database which data you don't have? I had to do this once, long time ago, in a Postgres. In Postgres today is easier, by the way. When I had to do it, it was not as easy. But my challenge was this. I was getting some data. I wanted to identify for which days a user didn't have activity. And for me, it was very easy to find in which days a user had activity. But in which days a user didn't have any activity, I couldn't do it. Because I don't have data for those days, so I don't know the days. So I have to do something like create another table to do an outer join and blah, blah, blah. Today is easier, but again, it's not as immediate. So something, and this is really the use case. I'm sending data every second or so. Tell me for which rows, for which devices, for which combination of columns, I haven't seen data in gaps or more than 1.5 seconds or something like that. So something I can do, I can use just the query I just showed you, sample by. I'm going to be sampling in 1 second interval, and you will see some seconds are missing. For example, second 21 is not here, so I'm getting data every second or so. We have a special keyword, fill, that I can pass several parameters. One of them is like fill with null values. So now, any record, this is empty. I could fill with the previous value. I could fill with the linear interpolation. I could fill, here for example, I can see these 2 rows are exactly the same, so that means one has been interpolated. I can fill with a constant, so that's the thing. You can actually use this to fill the gaps when you have any gaps with different strategies. Another problem with this kind of tricky is like, I have data, I want to, maybe from different devices, I want to see which is the last row that I've seen for every single device. And that sounds easy, but it is not. On SQL, you can do give me the last value. But if I want to have the last value for every column, I'll have to do select last from this, last from this, last from this, group by whatever. It's kind of tricky to do. Or you could do something like a window function. I want to do an over partition by the device, order by timestamp descendant, where and the rank function, and tell me the word where the rank is 1, and you will do it. But it takes a little bit. In QuestDB, you can just tell me, hey, from this table, give me the whole row, but only the latest by this particular column, or by a couple of columns. So you tell me, and I find, okay, for this, I give you just the latest, the latest row, the whole row, for a particular device, which again is very common in time series databases. I'm finishing here. This is the last query I'm going to show you, promise, for you to get an idea, which is like, what if we support joins? So no time series databases don't support joins. We do. Thank you. So what if I have 2 tables? They are ingesting data, but the timestamps are not exactly the same. If you have like very high resolution in timestamp, it's impossible to have the same timestamp, network latencies, whatever. So what if I want to join by approximate time? Or maybe in one table I have like, I am getting data every second, and I want to join with the weather table that I'm getting data only twice every hour. What if I want to find which is the closest record from this table to this other, independently of the frequency of each of those? We have a query which is called a type of join, which is called as of join, which does exactly that. For each record on the left table, is going to join for the record of the right table that happened exactly at the same time or before, and that's about it. So that's that's going to go, and it's the closest. So one output for each of those. If you want to have strictly before, we have the variation LT join, which doesn't check for equality, or you have the equivalent to a full outer join. For each record in one side and in the other, tell me the closest. We have the splice join, but it's basically the same thing. So here I have this query, which is joining the taxi rides for a particular day in the city of New York with the weather information. And what this is giving me is for each particular ride of this in this year, is telling me the closest matching temperature independently. For all of them, you see, for all of them, it's exactly the same because I have many trips starting the same second, but I have only, as I told you before, 1 or 2 entries every hour. So most of the, you know, thousands of records in one will be matching with one or the other until I have another record in the table. But that's the idea. You don't have to worry about those things. Again, trying to do that with relational data, you have to truncate the dates and start working with things. Not ideal. And the best thing is, like, you know, it works. We had one user a few days ago. He was saying, I have like this big machine and I'm trying to do this query, which is like, you know, well, actually 2 months ago, I tried to do this query with joins and it's slow. It's like, how slow? Half a second. Okay, I understand you are angry. It's taking half a second to join the table. How many rows you have? I'm just trying to join 3 tables. 1.6 billion records, 1.1 billion records, and only 2 million records in the other. So if I try to do a join between 1.6 billion records, 1.1 billion records, and 2 million records, why I have to wait half a second? Yeah, it's like, yes, why? And we're thinking, that's right. Oh, we are optimized for AMD and Intel processors, not for ARM. And he's using ARM. Maybe try a different processor. Okay. And maybe try to use an as of join, as I was telling you. Okay, I'm going to try. Oh, not bad. I went down from 500, you know, milliseconds to only 500, almost the same with Intel. Well, with the as of join, I went to, in an Intel, 300 milliseconds from 500. Oh, not too bad. 300 milliseconds from 500 milliseconds in percentage is quite interesting. Then we give them some advices. A couple of months later, we had forgotten already about him. He's like, hey, now I'm using a different machine and using CFS with compression, and guess what? We were in half a second before, not too bad. For joining 3 tables, 2 million records, 1.1 billion records, 1.6 billion records. So that's what I'm talking about. So those are actually, as of joining, are super cool. People from Postgres, 2 years ago, they were doing, like, you know, requests for comments. We are trying to implement as of join. And actually, there is a very good example in the documentation from QuestDB. So it's cool because we are stealing code from Postgres. They are stealing ideas from us. So we all steal from each other. That's called open source, and I really like it. So that's it. There are many reasons why we are very performant. The main one is like because we really care about performance. We have a lot of ideas to make it more performant in the future. You can use QuestDB as open source or in cloud. If you use it in cloud, you have $200 in credits. So you can just, you know, play with it for a while. We are open source. We love contributions. We love GitHub starts. If you have any questions, I'm going to be available today the whole day, now, and also in the drinks. So thank you very much and enjoy the conference.